Yes, we are live.
Okay, then. So, good afternoon, everyone. So, it's my privilege to introduce a remarkable piece of student research today. So, we have gathered here to witness a young mind who doesn't just learn mathematics but phrases its boundaries forward. So, he will talk about Farey sequences, which have fascinated mathematics for quite a long time now. So, their graphical representations, their patterns amongst rational numbers, their connections to topology, and even physics. So, let's hear it from Nikhil.
Thank you, Shaif sir. Thank you everyone for joining. In this talk, I present a three-dimensional Farey graph constructed on primitive integer triples. Classically, the Farey framework organizes reduced rationals by the determinant condition AD minus BC equals 1 or plus or minus 1. This topic links number theory, geometry, and continued fractions. Today, I extend this topic to three dimensions. Vertices are primitive integer triples considered up to overall sign, and two vertices are adjacent when the 3 by 3 determinant against a fixed anchor vector W equals plus or minus 1. The main results are an additive triangle rule that creates two simplices when the sums remain primitive, a linear Diophantine condition that makes adjacency in the 3D Farey graph explicit, and a degree dichotomy separating isolated vertices and infinitely many vertices together. I also present a non-adjacency theorem for primitive Pythagorean triples with computation explorations illustrating local structure and shortest paths within bounded subgraphs. There are additional results not included in this presentation. They will appear in the paper, and I'm working with Shayush sir on its completion. Next slide, please. So currently, this is my motivation. I would like to, here's the roadmap actually for the session. I would like to introduce the motivation from the classical Farey theory, basic graph and arithmetic definitions, and 3D constructions. In the classical setting, the reduced rationals A by B and C by D satisfy the absolute value of AD minus BC is 1, linking continued fractions, the Farey tessellation, and the group action of SL2Z on the hyperbolic plane. This, please see the historical references on the slide. They allowed me to work on this principle. Our 3D analog replaces the 2 by 2 determinant with a 3 by 3 determinant computed against a fixed reference vector 1, 1, 1. This produces an arithmetic graph on primitive integer triples, preserving the idea of minimal adjacency while revealing structure unique to the third dimension. Next slide, please. So what we will be doing today, I will be defining vertices that are primitive integer triples. I will be defining the edges and essentially generalizing 3D graph and understanding how they can be extended from two dimensions to third dimensions. And next slide, please. Next slide. So these are the terms that I will be defining. I use a standard graph language. A simple graph G equals VE has vertices V and edges E with no loops or multiple edges. Two vertices are adjacent if an edge connects them. The neighbor of a vertex and its degree are defined in the usual way. These are the terminology I will rely on throughout this presentation. Next graph, please. A path is a sequence V0 to Vk with each consecutive pair connected by an edge and all vertices that are distinct, and its path length is k. A subgraph uses vertices and edges from G, while the induced subgraph on W, which is a subset of V, keeps all edges G with both endpoints in W. These notations will let me discuss connectivity and shortest paths inside the bounded regions of our infinite graph. This is how I was able to use computational methods to make my 3D Farey graph. Next slide, please. So the Farey sequence Fn lists all reduced fractions a by b from 0 to with a value from 0 to 1 with b less than or equal to n, ordered increasingly. Two fractions a by b and c by d are adjacent if absolute value of ad minus bc is 1. When embedded in the upper half plane model of the hyperbolic plane, this graph forms a Farey tessellation which decomposes the hyperbolic plane into ideal two simplices. Next slide, please. This is the notation and conventions I use to define my 3D Farey graph. I define each triple ABC with its negative, so I only keep one representative from each pair, specifically the one whose non-zero entry is positive. For any triple DEF, I define its infinity norm as the largest absolute value among its coordinates, and I restrict attention to that norm as at most n. These conventions help avoid duplication and make finite computations in the 3D Fourier graph straightforward. Next slide, please. Throughout the presentation, I fix my reference vector W equals 1, 1, 1 as the anchor for the determinant-based adjacency. This symmetric choice yields particularly clean principles and formulas. I also define a triple ABC as primitive if its GCD ABC is 1. The vertex set is the set of all primitive triples ABC identifying as minus A, minus B, minus C to avoid duplications. Please see the definition as it appears on the slide. This is universal for our graph. I also construct an edge between vertices A and B where the determinant of A, B, W is plus or minus 1. Geometrically, this determinant is the oriented volume of the parallel pipe spanned by A, B, and W. And the plus or minus 1 condition is the minimal non-zero value mirroring the two-dimensional condition extended from the Farey sequence. Next slide, please. This figure is a two-simplex as connecting vertices A, B, and C with mutual adjacency, where you can see A is connected to B with a determinant of plus or minus 1, B is connected to C with determinant plus or minus 1, and A is connected to C with plus or minus 1. I also have this picture foreshadows the additive triangle rule that I will mention next. This lemma is one of the core principles in my 3D Fourier graph to enumerate neighbors. This rule states that if A is connected to B and C equals A plus B is primitive, then A is connected to C and B is connected to C. This proof is sketched on screen. We subtract matrices column 1 from column 2, so the middle column becomes B. And we get a determinant of ACW equals the determinant of ABW is plus or minus 1. Similarly, in the second case, with determinant of BCW, the same operation introduces a sign flip, giving minus or plus 1, which is the same as plus or minus 1 as per our condition. This is the additive triangle rule that enumerates neighbors in the Fourier graph, allowing me to compute various types of neighbors for a specific vector. Next slide, please. This is the key simplification of our entire construction. For A equals ABC, define alpha as C minus B, beta as A minus C, gamma as B minus A, such that the determinant of ABC, DEF, and 1, 1, 1 equals the equation displayed on screen, and we can simplify it to alpha D plus beta E plus gamma F. Hence, we can say that A is connected to B if and only if alpha D plus beta E plus gamma F is plus or minus 1, turning adjacency conditions into a single linear Diophantine equation. Moreover, any solution to this equation is primitive, since a common divisor greater than or equal to 1 would divide the right-hand side plus or minus 1, which is impossible, allowing a simple construction for the linear Diophantine form to establish adjacency within the 3D Fourier graph. Next slide, please. This is one of the main theorems put out in this presentation. Using the linear form, we obtain a dichotomy for degrees. A dichotomy is a set of only two possibilities. Either vertices are infinitely connected or vertices remain isolated. So using the linear form, we obtain that if A is equal to ABC and W is 1, 1, 1, if the GCD of alpha, beta, gamma is 1, then we establish that A has infinitely many neighbors. If the GCD of alpha, beta, gamma is greater than 1, then A is isolated. The proof idea is that we can use the linear Diophantine equation to express the condition where the GCD is 1, whereas when the GCD is greater than 1, the left-hand side is divisible by the GCD and cannot be plus or minus 1. Aside from the trivial 0-degree case, where A is equal to B is equal to C, there are no finite positive degrees in between, establishing the dichotomy of the degrees in the 3D Fourier graph. Next slide, please. I've used computational methods using Python to enumerate neighbors of a vertex 1, 1, 2. In this case, we have alpha equals 1. And through using the Diophantine equation formula, we're able to obtain a reduction to D minus C is plus or minus 1. This yields primitive families, where for sample eight sample equations and points are represented below. I identify DEF as minus D, minus E, and minus F to avoid duplicates. Next slide, please. Here is another example when alpha is 0. So here we have the unique case again where we reduce the Diophantine equation to minus E plus F equals plus or minus 1, leaving the D coordinate free, allowing for infinite neighbors. So this is an example of 8 solutions for a vertex A1, 2, 2. Next slide, please. Here is an example of isolation. For A equals 1, 3, 5, we have alpha, beta, gamma as 2 minus 4, 2, which is equal to 2, 4, 2, with the GCD of whereas GCD is 2, which is greater than 1. Hence, we see that the linear Diophantine equation is always even. Hence, it can never equal plus or minus 1, which leaves the vertex 1, 3, 5 in the Farey graph, which is primitive, as isolated, which is the representation of the isolation side in the dichotomy. Next slide, please. This is an example of a neighborhood of A100. Please look at this neighborhood diagram. When C equals A plus B when it's primitive, the additive triangle rule referenced earlier closes two simplicities naturally, and many incident edges appear around non-isolated vertices. This picture builds intuition for how adjacency and addition work principally well in the 3D Farey graph. Next slide, please. Now, I would like to define another core theorem in my presentation, the non-adjacency for primitive Pythagorean triples. A primitive Pythagorean triple is of the form 2xy, x squared minus y squared, x squared plus y squared, or its permutation, where x is greater than y, greater than or equal to 1, and where GCD of x and y is 1. Exactly one coordinate will remain even, while other two are odd, and that parity structure will be crucial in the non-adjacency result. Next slide, please. So, the theorem states that no two primitive Pythagorean triples are adjacent in this 3D Farey graph. If the even coordinates align in this position, then in the determinant case of determinant of ABW, every term is even. So the determinant case can never be plus or minus 1. Hence, in this mixed slot case, where we have the even coordinates in a different position, substituting the same parameterizations yields a difference in squares with odd factors that differ by at least 4. If we have odd factors which leads to plus or minus 1, the difference must be at max 2. But here we are getting 4. So hence the two primitive Pythagorean triples can never be adjacent in the 3D Farey graph. So I've actually used computational algorithms to enhance my explorations within the 3D Farey graph. Two algorithmic tools make the graph computable in bounded regions. As we have established prior that the 3D Farey graph is infinite, there has to be a way to reduce the Farey graph to finite bounds to understand and enumerate, understand the core properties of it, such as its degrees, how many neighbors are there, and essentially how many neighbors are there can be connected to each other. So I've used the norm-bound definition as prior to ensure that the vertices are up to a maximum value n, and I've produced the first neighbor enumeration. Given a triple A, compute alpha, beta, gamma. If the GCD of alpha, beta, gamma is not equal to 1, then A is isolated. Otherwise, enumerate all triples DEF in a bounded norm and keeping those satisfying the linear Diophantine condition. And canonicalize the sign, which means that DEF is equals to minus DEF, minus D, minus C, minus F. Second, the second algorithm wants to find the shortest path in an induced subgraph. So I actually have an example for you. So if we take A is equal to 0, 1, 3, and B is equal to 3, 0, 2, there is a path connected between them. The path is from 0, 1, 3 to 2, 2, 1. The determinant between those is minus 1, and from 2, 2, 1 to 1, 0, 1, which yields the determinant of minus 1, and from 101 to 302, we have a determinant of plus 1. Hence, these three vertices are connected within the subgraph, yielding a path length of 3. This is what we use to find a induced subgraph from the infinite 3D graph, establishing that we're able to find unique properties within them. Next slide, please. So this is what we understood from the 3D Farey graph. The determinant rule with W111 defines a 3D Farey graph on primitive triples, extending the classical Farey paradigm arithmetically. The linear reduction alpha d plus beta e plus gamma f equals plus or minus 1 drives the relative triangle rule and the degree dichotomy. Primitive Pythagorean triples never form edges between them, showing arithmetic selectivity in adjacency. Computations in bounded induced subgraph illustrate neighborhoods in shortest paths and confirm this theory. There are additional results as well, and I'm working on them, which I said for completion. Next slide, please. These are the references I have used to complete this work, and if there are any questions, I'm happy to take them. Next slide.
Well, thank you, Nitin. That was a fascinating presentation. This work really exemplifies what student research should be: curious, rigorous, and unafraid to tackle problems that we don't have solutions in the textbooks, in the school book. So it was a really good presentation given that you're quite young. Uh, thank you. Another round of applause. And hoping to work with you in the future and
Yes,
settle this.